Okay, this is lesson 15 of module 7. We're starting a new topic, and the topic is the Pythagorean theorem. And up through lesson 18, we'll be kind of revisiting some of what we talked about with the Pythagorean theorem in modules 2 and 3. We're going to look at some proofs, and we're going to look at some applications. So in this first lesson, we're going to look at two different proofs of the Pythagorean theorem. The first one based on similar triangles, which we actually saw in module 3. We're going to go through it together, and that's using these diagrams that are in front of you now. And then the second one is uses results from this theorem, but is more based on area. Okay, so remember, the Pythagorean theorem gives us a relationship between the sides in a right triangle. And if our sides are labeled A, B, and C, with the legs of the right triangle being A and B, and the hypotenuse being C, the relationship between the lengths of the sides would be A squared plus B squared will equal C squared. And so we've been using that result, and we've been finding either a missing leg length or a missing hypotenuse on a right triangle. And we've mainly been doing it where it comes out as a perfect square, but now that we know how to evaluate and estimate non-perfect square roots, we know how to find those to a certain digit accuracy of tenths or hundredths or whatever we need. We'll be doing that. We'll be taking those kind of a step further. Okay, but first we're going to start with this proof right here of the Pythagorean theorem. And every proof of the Pythagorean theorem is going to start with just a general right triangle. So if we have this right triangle, we want to know how can we prove that this is going to be true for any right triangle. And so that's the problem. So this first proof that we're going to look at that's based on similar triangles has us take our original triangle ABC and drop a perpendicular line to the hypotenuse from the vertex that has the right angle. Okay, so we just take and drop this perpendicular line in there. And so what that does is it divides the hypotenuse into two pieces, but still this whole length is C, and then we've got A and B. Okay, so the reason we're doing this is because it turns out that there are three triangles here now, right? There's the original one, which is right here in the middle, down here. But then we've got these other two triangles. So this one here that I'll outline in purple is this triangle here. And then the other one is this one here. And so that one comes over here. So we've got the original triangle and then the two triangles that resulted from putting that line in. So they're all three right triangles, and what we want to show now is that they are similar, that these are similar triangles, and so we need to look at them separately. Now to get say this purple triangle here down to here, you could think about the transformations that happened in doing that. It looks like there is not only a rotation but a flip. We had to flip it over so that we could put it in this orientation with the other two where it looks similar. But we could look at this and say this angle right here in this triangle is this angle here. So it's that angle in our original. So whenever we have, so if I want to think about, are these two similar, I could say, well, they both have this right angle. If either of these other two angles, if I can prove that they are congruent, then by the angle, remember angle postulate, then I know that those postulate, there we go. Then I know that those two triangles are similar. And so I have this angle here congruent to this angle. Therefore, all three angles have to be congruent and the triangles are similar. Okay, so remember angle, angle postulate, I can do that. Similarly, if I look at this triangle, which was translated down here, was also had to be flipped and rotated to be in this orientation. I have this angle B and a right angle. Therefore, because this angle and this angle are congruent to these two angles in the original triangle, I know that by the angle angle those two have to be similar. So what I have is three similar triangles. And one thing that you could do that we did in class back when we did this was we cut these out of a 3x5 card, and we could see that I took a 3x5 card and we cut it like that to have two congruent right triangles, and then found that line. And then you have this piece, and this piece, and you can rotate them around and reflect them and show that those three are similar, that by a dilation they would be copied right onto each other. Okay, so we have these three similar triangles now, and some of the side lengths, some of the original side lengths are labeled here. So this AC is the same thing as this segment right here. Its length is B. Okay, these other two lengths we don't know, right? They're not A, B, or C from the original. AD is right here, and DC is right here. So those lengths, we don't necessarily know what they are, right? But we know this is B. In our original triangle, of course, we have ABC still labeled. And in this slightly bigger right triangle here, we know that this hypotenuse is A, is length A, because it is this length on the original triangle, okay? But this DB right here is this length, and CD would be actually this one. Where's that? This one here, yeah. So that's that. So we have, anyway, we have these labeled how they are. So what we're going to do is because we know all three of these are similar, we can write some ratios between side lengths. Corresponding side lengths of these triangles are going to be in proportion. So I'm going to flip to the next screen so that I have room to do that. So here are the three triangles labeled with the side lengths. Okay, so I'm going to write those ratios. I'm going to circle these two in green, because in green I'm going to write some ratios that we can use to figure out something about these side lengths. So I'm going to use ADC and ABC first, or ACB, and talk about some corresponding ratios. Now, both of these triangles have the length B in them. So my ratios are going to focus on that length B. So I know that length AC corresponds to length on the small triangle. So this one here corresponds to length AB on our larger triangle. So that's one ratio of corresponding sides. Now I'm going to write another ratio of corresponding sides that's going to also incorporate this B here. So I've got AD proportional to AC, length AC. Okay, and I want to simplify that, so I'm going to use this. I want to to kind of cross multiply. So I've got length AC. So I know that if I multiply those two and those two, they're going to be equal for these ratios, right? Times length AC is equal to length AB times length, times length AD. Okay, and I also know something. I know that this length AC, which is used here twice, is equal to B. And I know that length AB is equal to C. So I'm going to substitute that. So this is, this right here would be B times B, which is B squared. That's B squared. B squared equals, and I can make another substitution here because AB is C. So this is C times AD. So C times AD. Because remember, I'm trying to get to A squared plus B squared equals C squared. So those are the lengths that I'm specifically interested in. So now I have this result right here, which is looking promising, right? Because now at least I have a B squared. So that's going to come in useful. So I'm going to switch to purple here, and we're going to consider ratios between those two triangles, which are also similar. Okay, so now notice these two triangles, I have this length here, BC, in both triangles. So I'm going to write ratios that incorporate those lengths, okay, as well as C is going to be involved here. So I've got length AB proportional to BC here, right? So I've got length AB and to, was it BC? Yeah, BC. That ratio is going to be the same as, so now I've got both of those lengths are known, right? They're C and A. They're from our original triangle. Now I want to incorporate this one. So I'm going to use BC on our large triangle here would be proportional to DB right here, length DB. Okay, so those are corresponding parts of those similar triangles. So again here, I'm going to have that if I write these cross products, so this BC times BC has to equal AB times DB. So let's go ahead and write that. So length BC times length BC is equal to length AB times length DB. All right, and again, I'm going to make substitutions with my lowercase ABC as much as I can. So this BC right here is length A. And BC here is length A. So this is going to be A times A, or A squared. So A squared is equal to, and I can also substitute this AB here, or wait a minute, AB, yeah, so sorry, our length AB here, not that one, right here, length AB is C, so this one here is going to be C, and this is times length DB. I see I made a mistake over here, didn't I? This, in our first one, I've got AB is the C, and this should be AD, and I wrote that wrong. So I'm going to correct that now. That's AD right there. Okay, because where did that one come from? That AD came from right here. So that's that length there. Okay, so AD or AB was equal to C, and AD is there. Okay, so now we have these two relationships here. We have something that's A squared, and we have something that's B squared. So we're going to use those, and I need another page, but we're going to use those relationships to go back and say something about the triangle as a whole. Okay. Okay, so I'm going back to our original illustration with our results from looking at those similar triangles. So here we have A squared equal to this quantity, C times length AD, or B squared equal to that, and A squared equal to C times length DB. So we're going to put that together because in the Pythagorean theorem, we've got, we want A squared plus B squared. So A squared plus B squared is going to be C times, the A squared is C times DB, length DB, and the B squared is just C times length AD. I'm determined to get that wrong. Okay, so those, so this equality is true, right? Because all I did was just substitute C times DB for A squared and C times length AD for B squared. So this should be true. A squared plus B squared should equal that. So now I'm going to simplify. So I've got, I've kind of got the left-hand side of my Pythagorean theorem. Now I want to work on this. So this is going to be C. I'm basically going to use the distributive property and factor out a C. So I've got length DB plus length AD, that quantity. So you can see why this is true, right? Because if I took and multiplied C in, like I was doing the distributive property, I would end up with this. So these two expressions are equivalent. All right, so now we've got one C. So now let's go back to our original triangles over here, which is why I wanted to be on this page to point to this. Length DB is right here. And length AD is this one right here. So here and here. So DB plus AD, those two lengths together equal C. Ta-da! So there's C times C. So what do I have? That A squared plus B squared is equal to C squared. Yay! So I could just carry this along here. So that's beautiful, right? I mean, I hope you could follow every step of the way on that. Now, I didn't make up this proof. I think it's pretty ingenious, and it relied on somebody saying, hey, what if we dropped a perpendicular here? We'd have all these similar triangles, and they proved it that way. So we have proven the Pythagorean theorem. Now, that's the proof we saw already. All right, so what we want to do now is we want to use these results and do another proof of the Pythagorean theorem that's based on area. Okay, so let me show you an example of what we're going to be talking about. And here is, you can see our triangle here in the middle, right? It's right here. It's a 3, 4, 5 right triangle. The leg lengths are 3 and 4, and we've put it on grid paper so you can see that. This length here is 5, which we can't count on the grid paper, but we know is true from the Pythagorean theorem. Okay, so if we think of the area model, 3 squared, this distance, say we would have 3 squared, if we just put this in the Pythagorean theorem, plus 4 squared is equal to 5 squared. And that's true because this is 9, and this is 16, and 9 plus 16 equals 25. Okay, so, but if we think of it as an area model of the Pythagorean theorem, here's this is 3 squared, right? 3 times 3 is 9. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, an area of 9. This is my 4 squared, and this is my 5 squared. So if you did this on grid paper, which would be kind of a fun exercise for you to do, I can draw my 5 by 5 square right here and notice that it's going to coincide exactly with this tilted one. You know, so I could actually just cut it out and match it up. And, you know, so we have 9, 16, and 25. So the areas, these two areas here, this one and this one, could be rearranged to fit inside this area, or exactly on top of, all right, if we cut these up in a certain way. So in essence, that's what this proof is going to do. It's going to show a way that we can cut this up so that I can show that this plus this is equal to that, which is the same as a squared plus b squared equals c squared. Okay, so that's just kind of a concrete example of what this proof is going to do. So here's the general, there's no numbers on this, right? So now we've got our A and B, our legs, and here's the squares on the legs, a squared, b squared, and the square on the hypotenuse, c squared. So what I have to show is that this area plus this area is equal to this area. And in order to do that, we're going to use some of the results from the similar triangles proof. Okay, so using this diagram, because it is really using some of the same arguments as the similar triangles one, it's just illustrating it differently. We're going to start by dropping that perpendicular. Let me use a different color. That doesn't show up very well. Dropping that perpendicular from our the vertex with the right triangle. Let me get this right though. So there's the those 2 marks. So the way out to divide this square into 2 rectangles. And what we're going to argue is we're going to be able to show that this part of the area of this square is congruent in size. It's the same size as this square. So this square and this rectangle have the same area, and this square and this rectangle have the same area. So we're going to prove that, because it's not immediately obvious, right? This one's skinny but long. You know, it's not immediately obvious. So we're going to have to prove that. But that's that. Our proof is going to show that. All right. So let's look at this. So this one. So in this diagram here, we want to show that this is this rectangle here is that part that I showed you. The other part will be, you know, will come off right here. Oops, I got my line tool. You know, it will be right there, sort of. And we'll deal with that separately. But first we're going to work on showing that this area and this area are identical. All right, so this is the notes that we wrote. I just copied and pasted from this part of our discussion, where we and it's the one where we compared these two, this pair of similar triangles. We got this result. So let's go back and see what that means in terms of area of the rectangles. Okay, so we have this a squared is, of course, this area here. And so on the right side of this equation, we notice that AB, or length BA or AB, is C. So here's BA, that is equal to C, and that's right here. So we substituted that. So we had C. And so this, so looking at this side of the equation, this would be the area of a rectangle whose sides were C and length DB. Okay, so if we come up here, we can see that this is just that rectangle. Here's length DB, and there's DB, and then we're going to draw length C right here. So this rectangle is this rectangle here, C times DB. All right, and then so we've shown that A squared is equal to this part of this square, which is actually a rectangle. Okay, so study that if you need to for a minute. I think it will make sense after you look at it again. So look back in your notes as to why all this is true based on our original triangle here and the similar triangles. But that's, you know, so these areas, these blue areas are identical. Okay, so we can do the same thing with, so this diagram leaves the blue on. Now we're adding the B squared and the rest of this C squared square, okay? So these yellow parts. So now we need to show that these yellow parts are identical, and to do that, we're going to go back to the relationships we wrote about these triangles, and I'm going to copy and paste here. Okay, so I'm going to copy and paste this green part here, which compared, which I wrote, those are ratios between the smallest triangle and the original triangle. And we'll go back, and we're going to show a relationship between the yellow areas there. So let's see if I can make this, whoops, cancel. So here's what we had, and it's going to be on top of part of our diagram. Okay, so there we go. So we ended up with this relationship that B squared is equal to C times AD. So for that one, B squared is, of course, this area right here. C times AD is going to be a rectangle with length C and length AD. That would, I could represent this multiplication with an area, using an area model. C times AD would be this rectangle. So let's see where we have that. So we have length AD here, and if we draw this out to a length of C, it would perfectly equal that rectangle there. So this is kind of C times length AD. AD right there. Doesn't want to let me write it. There it is. And this is the B squared. Okay, so we've shown that those two are equivalent. Okay, so once we've done that, we have shown that A squared plus B squared, so the combination of this area plus this area, is equal to C squared, because it's just the combination of these two rectangles added together is going to be equal to the area of the square that has sides C by C. So this length is C, and this length over here is C, and then this length here is also C because AD plus DB is C. So you see, this is an area argument, but it's the exact same argument in algebra as our similar triangles proof. Okay, so hopefully now you are fully convinced that the Pythagorean theorem is true for right angles. So let's just summarize what we did in this lesson. The Pythagorean theorem can be proven by showing that the sum of the areas of the squares constructed off the legs of a right triangle is equal to the area of the square constructed off the hypotenuse of the right triangle. So that's that diagram again. This one here. So we showed that this and this were equal, and we showed that this rectangle and this square have the same area. So in doing so, we proved the Pythagorean theorem by way of area. Okay, your problem set on this is going to have you writing some arguments for different triangles, and so do your best, but please study the answer key and make sure that your answers are complete enough and that you're getting the gist of what's going on here. All right, good luck with that, and we'll be back for lesson 16, which is going to get into what we're going to call the converse of the Pythagorean theorem. One more proof, and then we'll get into more application.